were taking a look at the CNN architecture. Okay, so we're taking a look at the whole idea of convolutional neural networks, right? And we basically discussed that, so we have many layers over here. So let's say we have CNN layer 1, then CNN layer 2 as an example, right? And so on. So essentially what we are doing over here is we are basically learning what we call features. So features are basically important characteristics of the data. So regardless the data is image or the data is text type of data, it doesn't matter. We still can use CNNs for it to learn what is important in the input data, right? So finally, once we have learned all the features, then as you guys saw, at the very end, we'll simply put a classifier at the end and then do the classification. We can also do regression if we wanted to. So anyway, this classifier typically is just like a regular neural network. Okay. So then we were taking a look at how do we put this together. As you guys saw, the architecture was a little bit involved. So in fact, I was half joking that whoever designed this should be given a Nobel Prize, if you remember, right? And I don't know how many of you looked at the news last week. See, the equivalent of the Nobel Prize in computer science is called the Turing Award. Okay, and just a couple of days ago, they announced the Turing Award for the last year, and it was given to 3 people, and one of them is Yann LeCun, and he's the founder of the Deep CNN. So, so anyway, he did end up getting the equivalent of the Nobel Prize, and of course the other 2 are also very famous people, Yoshua Bengio and Hinton, who's so anyway. So as we went through some of the architecture, so the beauty of this whole technique is even though at a higher level, it's a very simple concept. At a higher level, like I said, learn the features. For example, if we are doing face recognition, right? So the features might be the curves of chin or the nose or the eyes, and then start putting it together as we go into higher and higher layers so that we can distinguish one face from another. So at a higher level, it seems fairly commonsensical, but like I said, the amazing part over here is in the details. As you start going through the actual implementation, how it was put together, then not only as you put together, then you take a look at the back propagation. And even though you guys may say, oh, now we know back propagation, we can figure out the loss function, then start computing the gradients. But here, because convolutions are involved over here, the back propagation is not that straightforward. And if you make tiny mistake, maybe in your math or and especially in your implementation, you can easily spend months trying to figure out why it's not working. So the amazing part to me is if you already know it's going to work, right? Then you can spend day and night, debug it and get it to work. But in the beginning, whoever invented it, they didn't know whether it will work or not. And now imagine you try to program it and you run into errors, and now do you give up after a week or 2 weeks? Maybe. So that's the amazing part to me, that whoever did it was complete genius, and of course that's why they got the Turing Award. Okay, so to make sure, because this is such a fundamental importance, this is of such fundamental importance, as I said in the previous lecture too, it would be really nice for us to completely understand this inside out, because many of the newer architectures, as I will show you as we go along, are based on the concept of the CNN. Okay, so what I did is, as promised, it took me a while, I created a handout explaining the architecture, the backpropagation, and then, like I said, I'll give you my code over here, which is in C#. Okay, and your next assignment will be to translate it to Python. Okay, and when I wrote it in C#, it's very similar to how we developed our previous code, meaning a network class, a layer class, and so on. Some of you may not be as good in C#, but as long as you have some idea of C++ or any related language such as Java, as long as you can understand, you know, at a high level what the code is doing, the equations are there, the architecture, as I will show you, is there, so that you can easily implement it. So now let's take a look at, I didn't get enough time to put it on the website, but like I said, it's ready. So let me go over, is there a way to, are you trying to do, I'm trying to close this right part.
Oh, there is an arrow.
That arrow to the left?
Yep, that's an arrow. You can press that.
Which arrow?
On the line, the bar. On the bar.
On the
This part? No,
No.
the arrow one. Yeah, this part.
Yeah.
This part, go down on the middle.
Oh, this middle.
Yeah.
Okay, that's better. Okay. Okay, so anyway, so this is the example we did in the class. So I drew it a little bit better so that we can understand it. So let me go over a little bit of it, the backpropagation, and especially the parts which were, in my opinion, mathematically challenging ones. I will go over those again. So basically, what we have over here is 4 feature maps in the first layer, 6 in the next layer. Okay, we could put 8 in the first layer, 20 in the next layer, doesn't matter. Okay. So I thought that would be a small, meaningful example. So let me put the whole architecture there. So hopefully we can see. Okay, so anyway. So again, 28 by 28 image, feeding to, so this is our first CNN layer. So from here to here, you'll see this is the first layer. And then from here to here is the second CNN layer, right? And then we flatten it out. In the second layer, we had 6 feature maps, right? So once we go over here, as we discussed in the last lecture, there are 16 numbers over here. So if we went to each row and start putting the numbers side by side, so this will come out to be, as you can see, 16 numbers, right? Then 16 more numbers for the second feature map. And since we had 6 over here, 16 times 6, as you can see, total will be 96, right? So then, once we have these 96 inputs, so this is like a regular neural network. Okay, so this one, okay, as you can see, the weight matrix over here will be, suppose we decide to put 50 neurons in the hidden layer, 10 neurons in the output layer. So this will be basically 50 times 96, right? And this will be 10 times 50. If we convert it to a batch mode, then of course the matrix sizes will further get an extra input, meaning the batch size. Okay. Anyway, let's very briefly go through it one more time. So we had 4 convolutions going over here. So there's a 5 by 5 convolution that we apply to the 28 by 28 image. So as we discussed in the last lecture, what will be the output? 24 by 24, right? So same way, another 5 by 5 convolution, another 5 by 5 convolution, another 5 by 5 convolution. So we get 24 by 24 result of these convolutions, right? Then what do? We add a bias to each one of these 24 times 24 values, okay? So if the bias is 0.1 as an example, the same 0.1 will be added to all the values. So it's not like it's not like we are adding a different number to each one of these 24 by 24 values. It's the same bias. Okay. And again, intuitively, the concept is like this. Purpose of the bias is, right? If let's say it's a 2-dimensional data, so either to shift this data up or down, right? As an example, or move it in this. So essentially a single bias is basically adjusting the data slightly, okay? Then, so this is what I indicated by the plus part.
Summation.
Then what is this F over here?
Activation.
Activation function, correct? So this could be sigmoid, could be ReLU, could be tan, hyperbolic, whatever. So we are applying that to each one of these 24 by 24 values, right? So then in the equations, I call this convolution layer. The top superscript basically means the layer number, right? And then 1 means the first convolution map, second convolution map, third one, and this will be C4. All of them will have 1, 1, 1 over here. Okay, and then we go to the pooling layer. As we discussed last time, pooling is also called subsampling, right? So where we take the 4 values, and either we take the average of those or the maximum of those, then we go to the next 4 values and do the same thing. So the matrix size gets completely halved. So I call this CP, short for convolution, and then pooling. Okay, and then same superscript indicates the layer number, convolution layer 1, and then 1 over here, 2 over here, superscript will be still 1, and you can see like CP4 and 1, right? Okay, so this now is the first layer. So then let's say to each one of these we'll apply a certain number of further convolutions, right? How many convolutions should we apply to each one of those? It's decided by what? The number of features that we want, feature maps that we want in the second layer. So if in the second layer we want 6 feature maps, then to each one of these, how many convolutions will we apply? 6 of those. Okay? So there are 6 kernels over here. So I call this K1, 1, K1, 2. Meaning source is 1, destination is 2, source is 1, destination is 6. And at the top you will see there's again a number over here. So what does the top number indicate?
The layer number.
The layer number, okay? So as you guys have seen, you know, for example, when we did the softmax derivation or the batch norm derivation, see in all of these things, if you have it in your head, you'll totally mess it up. But if you have a picture and your terminology is completely clear, what you're trying to do, then the math will easily follow step by step. So, so having a consistent terminology that we understand makes sense is very important. So anyway, so same way, now let's go to the second output of the second feature map over here. Again, how many convolutions will we apply to this one?
6 of them.
6 of them in our example. Okay, once again, it doesn't have to be 6. If you decide to put 20 feature maps in the second CNN layer, then there will be 20 convolutions going here, right? Okay, so again, this is K2, comma 1, superscript 2, 2, 2, 2, 6, and 2, right? And same way, K4, 6 will be the last one. So again, 6 feature maps, 6 convolutions being applied to all of these. So how many total convolution kernels do we have over here? 24, right? 6 being applied to each one, and there were 4 of these. So 24 convolutions. Okay, so then what happens next is a little bit variable, but in the very basic CNN architecture, what we do is we basically sum the results of the convolutions from the previous layer to build higher level features, okay? So if you take a look at this sum, essentially what it's doing is getting the input from the first feature, first convolution that was applied to the first feature map, right? Then we go to the very first one that we had applied to the second feature map. So this one over here, as you can see, is coming from, I messed up the picture, let me see. This second one is over here. No, it's okay. So, okay, the first one should come from
The first one.
the first one, yeah.
It's on the top. It's on the top.
Should be this one, right?
Yeah.
That's the second one.
Right, the second.
It should be connected to the first.
The first one goes on the top.
That's right. First to
Okay,
first.
let me see. Okay, so this one is okay,
That's
right?
the first one.
That's the first one.
This is
Now,
the
this
second
should be coming from the first one of this one.
Second one.
Yes.
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 But that's where I messed it up,
No.
I think.
You,
Let's see.
it's fine actually. The connection is on the previous one. That should not have a connection. Yeah, that
This should not be there.
Yeah.
This should not be there. And this one,
Should
This
be
is
the
the
first
first
one.
one.
Should be the
yeah, this should go over here.
over there.
Yeah, okay. Okay.
We got
Yeah, so anyway, so yeah, the first one from each one of these goes over here. So how many total sums are we doing over here?
4 of them.
4. So 4 over here, 4 over here, right? So anyway, then we pass it through the activation, then we do the subsampling, then we flatten, and then the regular neural network. Okay. So I'll try to use a whiteout and try to fix the picture and upload it again. Okay, so hopefully the architecture makes sense, right? Okay, so now, like I said, after we understand how the architecture is put together, next thing, the most complicated thing over here was the backpropagation. So I've created detailed, I highly encourage you to go through each one of my derivations and see if it makes sense. Okay. Okay, and very briefly, as we are training this CNN, how many parameters do we have to learn? Okay, so going back over here, what's the value in all of these kernels? Because each one of these is 5 by 5 kernels, 5 each. They are randomly initialized. Okay. Further, there's a little trick to how do we initialize it randomly so that we get better training results. So I'll talk about that in a minute. Okay. So as you can see, 4 times 5 by 5, correct, will be the parameters that we have to learn through training. And how many biases over here? 4 biases. Okay. Then as we go further, there's nothing to learn over here, nothing to learn over here. Then we get to these kernels. There were 24 kernels over here. 5 by 5, so 24 times 5 by 5. So anyway, let me just show you the result to save time. Okay, so you can verify that I didn't make a mistake. 4 times 5 by 5 plus 4 biases plus 24 times 5 by 5 plus 6 biases plus the weights in the regular neural network, the biases, weights in the second the layer, the output layer, and the biases, right? So those are the parameters that through training we'll initialize these randomly, then through training we will learn those. Okay, how do we initialize those? Okay. I mean, one possibility is just randomly initialize all the kernels between -1 and 1 or 0 and 0.5 or whatever, right? LeCun wrote a very nice paper, and I'll put a reference to it. I forgot to put a reference to it, through where I took these this data over here. So basically, as you can see sort of from these formulas, according to him, and there was a nice mathematical analysis done over here, I'm just giving you the plain summary of it. The plain summary of it is, if you have 4 feature maps, and the kernel size is, let's say, 5 by 5, then you and the number of input prior to it is 1. So then, because there's only one image being fed over here, then you uniformly initialize the kernel between plus minus this particular value. So in their paper, they argued this leads to better training results. Okay. Anyway, let's take a look at, so remember the top subscript is the layer number. So let's go to the kernel for the second layer. Okay. The kernel for the second layer, how many feature maps we have over here? 6. How many feature maps were there in the previous layer? 4. Okay, so anyway, so this will become, I think maybe I made a mistake. This should be 6, I think. Yeah, so that should be 6. Okay, anyway, same way they have some recommendations for the weights and the biases, and I'll double check these. So based on my memory, this is what it was. Okay, so before we do the back propagation, let's take a quick look at the forward pass. Okay. Okay, so now let me first show you the picture momentarily. So now what we are looking at is we're looking at the equation of one of these, C1 of 1, right? As you can see, there's an activation function applied to the convolution, then a bias is added to the convolution, right? So first we'll apply convolution, add the bias, then whole of it will apply the activation function. So, okay, so in the terminology that I'm using, by the way, I'm using the letter M for the number of feature maps in first layer. So in our example, M will always vary 1 to 4. Okay? Then N, as you can guess, is the number of feature maps in the second layer. Okay. So this way it will be less confusing as we write the map. Okay, so first let's see. So what will M vary over here in this equation?
From 0 to 4, right?
1 to 4.
Oh.
Okay, I'm starting the starting index as 1 instead of being a 0, but when we write the code it will be 0. Okay. Anyway, so let's see if this makes sense. Can you guess what I is?
Image 28.
That the input image, which is 28 by 28. This is the symbol we use for what?
No.
Convolution, right? With the kernel. Okay, on purpose I call this, even though there's a single kernel being applied to, so if this was the image, right, we apply a 5 by 5 kernel and we get a 24 by 24 as an example, right? Okay, I named it as if this is a two-dimensional array of kernels. Okay. Why? Because what if we had 3 color channels over here? Red, green, blue, right? Then to each one of these we'll be applying a 5 by 5 kernel. So as if the 3 previous feature maps are being fed to the next one. So this way, once we write the code, we can generalize it completely. So then this will vary also 1, 2, and 3, the first index over here. Okay. Anyway, so hopefully this makes sense. Each image is being convolved with the kernel, and M varies from 1 to 4. So how many kernels will there be? 4. So for example, if I put M equal to 2, then you can easily see, what am I saying? C2 of 1 is computed as activation function of do the convolution with
K1 of 2.
K1 of 2 of 1, right?
Plus B.
Add the bias
2.
B2 of 1. So it does hopefully make sense. Okay, so convolution, as we discussed in the previous lecture, because our kernel is 5 by 5, typically we go negative infinity to infinity. So this is the standard formula for the discrete convolution. So any value ij over here will vary I minus u, j minus v, u, v plus vm. So basically, all I did is expanded this into the actual convolution formula, right? Okay. And so that's the, so hopefully this one is, so now do we know how to compute all of these in the forward pass, right? C4 of 1. Okay, so these are done. Now we need to define subsampling.
Pooling.
Or pooling, so I call this CP. So mathematically speaking, that's pretty easy.
A quick question. What's I and what's J?
Ij is, so let's go over here. Okay, so because we have a 24 by 24 output over here, Ij will vary 1 to 24. Yes.
This equation, when we say I minus u and j minus b, so if I and j are 0, 0 at the beginning.
In this case, the starting index is 1.
Okay, so if it's 1, and if u and b are 2, for example, so it will be 1 minus 2 and j, 1 minus 2 and 1 minus 2, which is minus 1.
Yeah, but see, as we discussed, like if I draw the picture, if this is a 28 by 28 image, right? So remember, when we put the kernel over here, that's the first time it will produce the output. So meaning we don't start the kernel here, then these will have negative values.
In this case, the starting index is 2.
Starting index is 2, yeah. Yeah, this equation is, yeah, from index point of view is not 100% accurate because this value does need to vary 1 to 24. Okay, but yeah, the starting index, yeah, probably be better to have it vary from 2 to 26 and then subtract 2 from the final answer to adjust it back.
Maybe we can do I plus u and j plus v. Will it work?
We don't want to change the sign because then that's not the proper definition of the convolution. But maybe think of it, we vary it from 2 to 26. Whatever answer we get, then we shift the I and j by 2 further to make it 1 to 24. Okay. For the pooling, so once again, 2i minus u, 2j minus v, and you can later on verify that all it's doing is basically adding these values. then dividing by 4, then moving to the next set of two values. So this is not important from backpropagation point of view, but simply, a compact description of the pooling operation. Okay. Okay, so now let's go to the second layer. And so let's take a look at how Cn of 2 will be computed. Okay, so once again in the terminology, n is the number of feature maps in the second layer. So in our case, it will vary from 1 to 6, right? So let me show you the picture quickly, and then hopefully this equation will make sense. Okay, so now we already did this. Now we are looking at this part over here. How will we compute this from here, right? See, as we discussed before, how many additions were being done by applying convolution to these? Four were being convolved over here, right? Okay, so now hopefully if you see this equation, okay, so do you see like 4 summations going on over here, right? And as you can see, this is the convolution basically. Okay. So in this particular example, n is going to vary 1 to 6. Okay. And m, so for example, so if we m varies 1 to 4, right, in this summation over here. So you can see, for example, what it is saying is C1 of 1 is being convolved with, if you take a look over here, so let's say we are looking at C2 of 1, sorry, C2 of 2. So what is the output of the, or let me make it easier. Let's take a look at C1 of 2. So how will what kind of convolutions will be done with C1 of 2? Okay, as you can see, C1 of 1 will be convolved with which kernel? K11 of 2, correct? K11 of 2 plus C2 of 1 from the previous layer, the second one will be convolved with K2 of 1, do you guys agree? Yes. And similarly, C3 of 1 will be convolved with K3 of 1, and so on. C4 of 1 convolved with K4 of 1. Okay, so that's all this equation is saying. So for any Cn, we can compactly describe the convolution and the summation through this equation. Okay, so now the rest of it is easy. After we have described how the 4 summations are being done over here. So after we know how to calculate this, then what's the step over here? Pooling. So we again have a regular